So we're going to continue on with Module 11 and do Section 2, which is Module 11.2 here. Talk about tuning some controllers, saturation, and state variable feedback. This relates to Sections 11.3, 11.4, and 11.5 in your book. Most of this lecture, we're going to focus on tuning controllers and talk about a couple practical applications and some research examples that I've done in the past utilizing some of the key equations and material from this section in this module. So we've already discussed a few different ways in order to compute the appropriate gain values that we're going to use for a controller. Well, in practical applications, these gains should be adjusted from their computed values in order to determine how sensitive the performance needs to be to the specific gain values. Now, one of the best ways to improve the performance of a system is to actually tune the controller. So what is meant by tuning? Tuning also means computing a preliminary set of gain values based on experiments with the plant. So a lot of times before we use computers, this was just done with trial and error. So you'd go out there, you'd have a rough idea from your calculations of what some of these gain values could be for the controller, and you'd go out there, run a test with that set of gains, see what the performance output was. Did it do the desired results? Does everything turn out right? And if it was a little bit under, a little bit over, tweak back and forth with those gains in order to tune the controller that way. So trial and error was one method of tuning your controller. So now we're going to talk about a little bit more systematic approach to that and using some feedback from information from the motor, the plant, the system, whatever it is, back into the controller in order we can evaluate itself in almost an automatic evaluation process to tune the controllers. So the book discusses a couple different methods. One method that we talk about here is going to be the process reaction method. Now this is going to rely on the fact that many processes have an open loop unit step response. And this is shown here down below, so we can see on the x-axis here we have our time, and our y-axis we have our open loop step response here. So the process signature is characterized by two different parameters, our R and our L, where the R is going to be the slope of the line tangent to the steepest part of the curve. So we can see that right here. There's our slope of the line to the steepest part of the curve, and there is our R value. Right there is the slope of this line right there. And then our constant L is going to be the time at which this line intersects the time axis. So we can follow this line straight down here and see that it intersects the axis right there. So this distance L from our origin point right there is going to be that time that we're interested in, or our constant L. So another method we'll touch on briefly here that's covered in the textbook is the Ziegler-Nichols process reaction method. Now this method assumes that the process is linear and therefore scalable. And this may not always be the case in practical application, but it does make that big assumption in order to use this method. So this table here gives the recommended controller gains associated with the control mode type here, either P control, PID control, or PI control that we see here under our control mode. Then it gives us also our controller transfer function shown here in this section here. So next we're going to take a look at a couple different examples and relate them to some practical applications and some research and some projects that I've done. So if we're looking here, kind of a generic diagram here, we have for the tuning of the motor with a speed controller. So in this example here, we have some motor that has a desired output, some RPM that might translate to a set speed of, in my case, a linear drive or a cart on a linear drive, but the motor itself is going to have some desired RPM that we're going to need to achieve. Now there's going to be certain things that are going to be causing a disturbance in this here. The weight of my antennas, the friction of the bearing and the guides, alignment, things like that are going to cause disturbance. So those things are going to change how the speed of the motor, or the RPM of the motor right there. So we have our microcontroller here that's setting all the information here, sending it to our motor driver, and our motor driver is then sending that information to control the speed of our motor. So we're going to need some type of feedback from our motor here to tell our microcontroller what it's actually experiencing. So there's a couple different ways that we can do this. We'll talk about an open loop and a closed loop when we do it here. But what I'm saying for my project here is I decided to put in a manual potentiometer. So this is going to be my speed controller on my system here as a potentiometer. So even if there was no feedback loop and this was an open system here, I could change the speed by simply turning this potentiometer here, sends that information into my Arduino or my microcontroller. That information is then sent to the motor driver, which is connected to my motor and changes the RPM. So just by turning the potentiometer here, I can adjust the RPM. But I need information on what that RPM is. So how do I find that? Well, that's right here. I could have a display output. I could measure distance and time of the actual cart. I could look at a couple different things to get that information. But the other way that we could do this is with a feedback loop. So we could put an encoder on this motor here, and that information from the encoder would be our feedback sensor, which then loops back, and we could send that information back into our microcontroller. So we could bypass our manual adjustment through the potentiometer here, and we could send that information directly in the microcontroller and say, okay, we're shooting for 10 RPM and we're at 9.5 RPM, therefore make the adjustments in the code here in the gain, and then send that information to our motor driver, to our motor, and then double check it again, and it's going to constantly checking itself. So even if we get these disturbances that may be slowing it down, speeding it up, the friction's increasing, decreasing, loads changing, vibrations, anything like that, it's going to have this feedback loop that makes a smart system so it can automatically adjust regardless of what the disturbances that are coming in and affecting the speed of the motor. So what I'm going to show here is a simplified version of the diagram I showed in Module 10 for my linear drive. So I'm just going to talk about the motor control portion here, related back to the previous slide where we talked about different types of feedback and how we could control the speed of the motor or optimize the system performance here. So what we can do here is there's my potentiometer or my speed controller wired directly into my microcontroller or my Arduino board here. And this Arduino board is then connected over here to our motor driver, and our motor driver then connects to our motor. On our motor here, I have an encoder that gives feedback back along here to our microcontroller here. So this is our feedback loop here, and we can see that in the diagram down below here, which is the same as the first page there, where we don't necessarily need to use this potentiometer anymore if we're using the information provided from the encoder to send back into our Arduino board. So we start up the system. Our motor starts spinning at a set RPM here. Our encoder here is telling us that the speed of that motor and the RPM, sending it back into here. This information is then sent into our microcontroller here, and it says, okay, we're supposed to be at 10 RPM, we're only at 9.75 RPM, therefore make the adjustments, change the gain, send that over again to our driver here, and then the driver sends that information, the correct voltage over to an amperage over to our motor here, and changes it, and we get that feedback again right there. So we have a constant feedback loop going through. So even as we increase the load on this, or we start getting some disturbances on our motor here, it maintains a constant speed. And this is crucial for this project here. This is dependent on the antennas moving at a constant speed and knowing exactly their location. So this feedback loop here, this controlling the speed of this motor, becomes very crucial for determining the position of our antennas at any given point during our testing. So shown here in this slide, I have an overview of the system with all of our electronics in a black box. So what I've done here is I've taken that block diagram and associated it with the physical components of this linear drive or motor controller system here. So what we can see here is we have all of our black boxes, electronics down here in this green boxed area showing our system there. Now from our system here, this contains our motor driver, our microcontroller, and our potentiometer to set the speed manually here. So we can run this as an open loop or a closed loop system here, depending on what we want to do. If we want to run it as an open loop system, we can simply turn this potentiometer to change our speeds right there and keep tweaking it by looking at the output and then changing the speed of it, then that could take into account all of the disturbances we may be seeing on the system by manually controlling it with this potentiometer here. Now, the other option here now, as we can see, this comes out of our black box up here, and this connects over down here to our motor right here, and it actually feeds back off the encoder and then back into our electronics block here where it connects to our microcontroller there. So we're getting that feedback information from the encoder on the other side over here of our motor. So this is going to give us that feedback. So we can see down here our disturbances might be something like the tension in this belt, the alignment of these gears and pulleys, or if we keep going over to the side that we can't see, it may be something that's changing, putting a slight tweak on the load of the antennas, which is increasing the friction and the alignment on the rail system that's guiding this and making it not so smooth a motion, and the friction increases, so therefore we need to bump up the amount of current going to our motor to make up the difference because it's slowing it down. So we have that constant feedback from the encoder going back and forth between our electronics box and our microcontroller, letting us know how to adjust to maintain that constant speed. So taking a look now at another example here, we worked on a project where we wanted to look at soil conditions, in particular the moisture content of soil. Now, this is important for a couple different reasons for us. For our practical application, we do a lot of ground penetrating radar testing where the dielectric properties of the soil greatly affect our testing data results. So if the moisture content is too high, it's going to change our dielectric properties. We might not get good penetration of our radar, so therefore we can't see the buried objects that we're looking for in our testing. But for this system here, we're going to simplify it down, not worry about the radar side of things, and we're just going to talk about this in order to control a rotating magnet. And we'll talk about it with and without feedback, and we'll have a couple different systems and how we can get that feedback information to optimize our system and change our controller. So what we have here as an overview of the whole project is we have some moisture sensor that's in the ground. Now this is going to have a sensitivity adjustment on it in itself. So it in itself has its own controller. But we're going to just ignore this for now, simplify down our example. We have a moisture controller that's already set, and this is going to head into a relay. Now this relay, based upon the information we get from the moisture sensor, is either going to turn on and off a power supply that heads to a rotating magnet. So basically what this is saying is if a certain moisture value is reached based upon our settings here, our threshold values, it's going to send out a signal to our relay, and it's going to click that either on or off. Now, in between here, what we ended up doing was putting in an Arduino system, a microcontroller, so we could accurately program in, okay, the threshold level is below this or above this, go ahead and click the relay on and off and send power to our motor, our DC servo motor, which is causing a rotating magnet here. So once this magnet rotates, what we're then doing is we're picking up the speed of that rotation on a magnetometer. So this is the second part of our system here, is the receive side of this here. Because this is buried underground, we need to pick up the information above the ground there. So we have this magnetometer that we can move around and say, oh yes, the magnet is rotating, therefore we have a certain moisture content that leads us to make decisions on whether or not we can scan that ground, or we need to adjust the moisture content within the soil before we can do any testing. So that information from our magnetometer is fed into an Arduino. We need to do some FFTs on that information to go from time domain to frequency domain. So we'll get into that again. So we talked about that a couple lectures ago, and I know several students had questions on where this would be a practical application. So I'll spend a little bit of time talking about that. Then that information in our Arduino is then processed, and the results of that are transmitted through a LoRa shield wirelessly to a receiver some distance away, and LoRa stands for long range. So this could be a mile away. We could be picking this up, reading it in through another Arduino, processing that data, and sending it to the internet, the PC, data storage in the cloud, where we can analyze all that information. So taking a look at some of the physical hardware that we have here, here is our moisture sensor that we're going to place in the ground to measure the properties of the soil. Here is our amplifier right here. So this is what we talked about. We can adjust that gain manually on that amplifier right there to set our threshold values for what we consider our levels that are too moist, or too dry, not enough moisture content. All that information there can be adjusted by this here. This information was then sent to an Arduino with a motor controller shield on it. So there's our microcontroller and our motor controller shield that connects to our DC motor with a rotating magnet on the end there, and all the programming of our microcontroller is done internal to here. So a couple different ways that we can do this, and we can tune our controller. One, we can manually tune the controller right here. Again, we take a look at the information, that whole trial and error method here. Okay, yes, the moisture content of this, and therefore we need to adjust our amplifier here in order to change our threshold values that get sent into our Arduino. We could also program in the threshold levels into the Arduino there. So if we don't want to keep manually adjusting this on the actual amplifier there, we can then modify it within Arduino here and change it by changing the code that tells us when to send the signal over to our rotating DC motor and rotating magnet. So now let's take a look at our moisture sensor test bed here. So this test bed here, we can see we have a 2D side view showing all of our equipment and how we're acquiring the data here. So over here we can see this is our moisture sensor and relay, which is connected down here to our rotating magnet that's buried under the ground. Now this is going to send our signal back up to our receiver right here with a LoRa transmitter that's going to transmit this a set distance away. We could be over a mile away from this here, receiving all that information from our rotating magnet. So it's basically the Arduino here is performing an FFT on our data that's coming from our rotating magnet, backing out a frequency of that, and based on the information we're getting from that frequency, we're sending that in small data packets, very small data packets across the wireless LoRa network to our LoRa receiver over here, which goes onto our computer or our network right there. So next thing I want to do is look at this in a little bit more detail for our rotating magnet moisture sensor controller. So we're going to take a look at this as an open loop system and a closed loop system. Now if we're talking about an open loop system, we're going to be manually setting the code on our microcontroller in order to control the speed and to control when the motor kicks on and off. So how do we do that? Well, that means we're not going to use a sensor at all to alter the behavior. So what we're going to do is just look at this here and either come in to our microcontroller and say, okay, things are a little bit off with our settings for our controller here, so therefore we need to manually get in, change the code on that there, and get the motor, make sure that the motor and relay are clicking on at the right threshold levels in order to rotate our magnet. Now, a closed loop system right here is something where we can say, okay, now I can automatically take the information from our motor here using a sensor, in this case here maybe an encoder, and send that information back through a feedback loop back into our microcontroller to make the changes that we need to the controller to change our threshold levels or the rotations per minute, the frequency of our rotation of our motor right there. So a closed loop system has, again, this feedback loop, in our case a sensor or an encoder, and it monitors the speed of the motor or whether the motor's on or off, and adjusts the voltage to speed it up or slow it down, or it adjusts the threshold levels in our microcontroller to tell us when to click our relay on and off. So let's take a look at the system as a whole here. Before, we'd really only looked at this top subsystem of this open loop system here, which is basically just a motor controller. So let's look at this in the most simplistic way we can here. We have a moisture sensor here. This moisture sensor is going to have levels, threshold levels programmed into it. When those levels are reached, it's going to tell the microcontroller to send voltage and turn on a relay or trip a switch on a relay, which then sends that voltage from the relay into our motor, which causes it to rotate. Now, we're going to think of this in the most simplistic case here, where this is going to be set at 1 RPM. It's either going to be on or off. So basically, this is just a binary signal coming out of this by a rotating magnet that's going to be received by a magnetometer. So let's just say the soil was too dry. So once that information there said, hey, our moisture sensor here, the threshold is below what we consider to be enough moisture content, so it's too dry. So therefore, it clicks this, sends us the microcontroller, clicks on our relay, spins our motor here, sends out a rotating magnet, spins the rotating magnet at a set frequency. This magnetometer picks it up at that frequency, sends that information to another microcontroller over here, performs an FFT on that information there to back out the frequency of that rotating magnet. This information from our rotating magnet here and our FFT is then sent via long-range wireless communication through a LoRa shield. Now, this LoRa shield is then sent to another receiving LoRa shield over here on another Arduino, where that information is then passed along to a monitoring station where they record the statistics and look at it, and a decision is made here. Now, this can be an automatic decision. It can be somebody actually looking at the data saying, okay, now go ahead and they click a manual button. Either way, that information is then sent back to our microcontroller, out through the LoRa shield, transmitting it over to another Arduino LoRa microcontroller setup over here, where that information then goes to the microcontroller saying, hey, we've received information from the controller, the monitoring station here, that says our soil content is too dry. Therefore, you need to click a relay to turn on our sprinkler system and add more moisture to that soil. So this is our feedback loop of this whole system, which is comprised of 4 subsystems here that then says, hey, let's send some water back into here. And then our moisture content is then reevaluated by our moisture sensor here, and the process is repeated. Now, in this case here, for the simple system, if the moisture content is met, our minimum qualifications for that, for our threshold levels, it won't send a signal to the relay to click it on and spin the motor. So the motor just sits there, and the magnetometer doesn't pick anything up. Now, a slightly more complicated way to view this is rather than the motor just being in on or off position with one set frequency, maybe there's different things that we want to decide to do based on different threshold levels within the soil moisture content. So maybe there's 3 or 4 things we want to do, or maybe the moisture content will dictate how much the sprinkler water comes out of the sprinkler, things like that. So in this case here, what would happen is the information from a moisture sensor is then sent to our microcontroller. Now, based upon that information, it categorizes it and says, okay, I'm in this moisture content, therefore I'm going to spin the motor, send this amount of voltage to the motor so it rotates at this set frequency. Okay, it's a little bit higher, so therefore it's going to rotate at a different frequency, a 3rd frequency, a 4th frequency, a 5th frequency. So now we can send out more information that corresponds to our moisture content from a rotating magnet. So now the magnetometer down here is picking up this information in the time domain signal from our RPM of our motor here, and it takes that information, performs an FFT on it, and says, okay, what frequency is it spinning at? Once it sees that information from the FFT and understands what frequency it's spinning at, then it says that back to this microcontroller, says, okay, this frequency means that this is happening and it's this moisture content in the soil. So it sends that information now over the LoRa, the long range network, to our monitoring station, could be some miles away here, where they look at this and say, we're at this frequency here, which corresponds to, and that information is all stored in this microcontroller for what frequency we're receiving here means it's this moisture content. So this moisture content is then sent to our recording station where somebody looks at that and can live view it, or it can be an automated process. And they say, okay, well, we're at this moisture content, so therefore, go back to our microcontroller, send out information over here to our receiver over here from our LoRa receiver on the shield on our Arduino there, and tell it to do some task, some function of our sprinkler system here. So it may be to kick the sprinkler on a little bit longer, it may be to increase the flow of water coming out of it, all types of things, or there may be another application coming out of here to dry the soil. So a couple different versions of this system here, but we can see how this feedback loop becomes very important here, and all for a simple task of controlling the moisture content of our test bed. So talking about our FFT and the need to go from our frequency domain and time domain back and forth between them, this up here in our top graph is the information that we get from our magnetometer. So we see a rotating magnet. This is what our magnetometer picks up. Now it has an X, Y, and a Z, depending on the orientation where we set down our receiver. So there's some averaging done within there depending on which axis we're looking at here. In this case here, we're looking at our x-axis here, and we can see we have this function right here oscillating in our time domain. Well, we want to know what the frequency of that is, so we use a fast Fourier transform. The Fourier transform converts the time domain oscillating field that we're seeing up here to the frequency domain and allows for the determination of the frequency of the spinning magnet. So our spinning magnet, we can see here, therefore it's rotating at 2 Hertz. So we've done that FFT, so this information here now pops up as just one frequency peak. Now, if we were talking about different frequencies indicating different soil moisture contents there, we might see, okay, this right here, if we see a frequency of 2, that corresponds to a moisture content here, so therefore we don't need to do anything, we're at the right moisture content. But if we see now a spike here when the frequency of the rotating magnet is at 6 Hertz, that means it's too dry and we need to turn on our sprinkler system. So all of that is why it's very important now that we're using this FFT to go to our frequency domain from our time domain.